record the second one. Notes and occasional practice problems. So with that in mind, I'll always upload stuff to my personal website. And I'll always post links on Piazza to those. Do we have any questions before we move on? At least he's not a Man City fan. Yeah, I don't know how to feel about that. Ever since like Messi, I'm also a Barcelona fan since Messi might move to Man City anyway. With that in mind, let's move on to the bulk material for today. So even if you didn't go to lecture, transistors. So what are they? I think for the main context of E16B, all you need to think about are switches. They're really these electrical devices that just switch on and off. And the second functionality of transistors are amplification, but I think 16B doesn't spend enough time on transistors to actually talk about that. So I think you may see a little bit in the lab on this, but just know that amplification is another really important thing that transistors do. And again, just some common terminology that you may have seen in lecture or may have just seen online before taking this class. We have this term called MOS, which stands for metal oxide semiconductor. And this is really just referring to the material that these transistors are made out of. And FET stands for field electric transistor. And this refers to like, I think something related to like the field, the electric field for the transistor. I'm not too sure. And then BJT, this is another common one that you might not have seen in lecture, but this will definitely show up in the lab later. And the BJT is one of the most important transistors in circuit design. So the BJT stands for the bipolar junction transistor. So if you ever see these abbreviations, these are what they stand for. And the main transistor we're going to be seeing in this class is the CMOS transistor. And the C in CMOS, MOS stands for metal oxide semiconductor, but C stands for complementary. And complementary here means like these two types of transistors kind of complement each other. I think someone talked about this in lecture yesterday, where you have the NMOS transistor and the PMOS transistor, and the two are sort of mirror images of each other. And the N in NMOS stands for N-type, or sometimes N stands for negative, and this refers to kind of the electron behavior. And the P stands for P-type, and P stands for positive, and positive and negative really refers to like the charges on the electrons and holes. But all of these things are stuff that we leave to upper div circuit classes, and they're just there for your interest, and most of it will be out of scope. So what you really need to know are these two diagrams, and the fact that the PMOS transistor has this like little bubble here. And I think someone in the earlier discussion actually asked, what does that bubble stand for? And I wasn't sure, but luckily someone was able to say, I think the bubble stands for a hole. And I think that probably is the correct judgment, where the hole in the electron, it's kind of their firm notation from circuit designers. So the hole is always the easiest way to distinguish between the two. All right, do we have any questions before we move on to something else?
Is there a reason why the drain and source are flipped between the two?
Yeah, that's a great question. I think it's really just convention that like whenever we build CMOS transistors, the PMOS will always be on top and the source will always be connected to like the top of the PMOS. But this brings up a really good point that for both of these transistors, no matter what, source, actually this is not correct. For the NMOS, source is the higher potential. And I messed that up again. Drain is the higher potential. God, 4 times teaching this class, you think you get this right. And source is the lower potential. And for the PMOS, source is the higher potential. Drain is the lower potential. And what this actually means is, if I were to apply 5 volts to the drain and 0 volts to the source, this is saying this is the drain, this is the source. Whereas if I were to flip the polarity and say this is 0 volts and this is 5 volts, what this is actually telling us is these are incorrect and that this is the actual drain, this is the actual source. So before applying any voltages, it's really ambiguous which side is the drain and which side is the source. But you can always identify which is the drain and source depending on which voltage is higher and lower. Does that help answer the question?
Do they have different behaviors?
Yeah, so they'll have different behaviors usually, or different behaviors as in
mean like the PMOS and NMOS having different behaviors?
yeah, the two transistors will always have like different behaviors and they'll have like opposite behaviors. And I'll talk about the behavior of the switching in the next slide. So I think these are always things you just write on your cheat sheet, no matter what. Like you're always going to forget these. So, I mean, like for what it's worth, I forgot it today. So,
for the PMOS diagram, you've annotated that notice the bubble in the NMOS. Do you mean PMOS?
Yep.
Okay, thanks.
All right, if we don't have any other questions, I shall move on. So why do we care about transistors? And I don't know if lecture talked too much about this. I know lecture talked a lot about power as I was like glancing over it. But some people may call the transistor the greatest invention of the 20th century. And this is really because these like little building blocks, the NMOS and PMOS transistor, form your computers. And today in discussion, we'll see how to build logic gates out of these CMOS transistors. And using these logic gates, you can actually build an entire CPU out of them. And if you've taken 61C, you might remember the Logicin project where you took all those like logic gates and built an entire CPU. So it's kind of why transistors are important. You can build computers using them. And another cool thing you can do with transistors is you can build a digital clock out of them. And what I mean by a digital clock is something that like switches from like high to low. And you can build these by just chaining a bunch of NOT gates together and taking the output of the last NOT gate and like feeding it into the input of the first gate. Yep, redstone clocks. So you can build clocks out of transistors. These are called ring oscillators. And you can also amplify signals using transistors. So everything they told you in 16A is kind of a lie, where they kind of like talked about like non-inverting op amps and like inverting op amps, but really all of these op amps are built out of transistors, and like one op amp actually takes up like 13 transistors. So you could actually build an amplifier using like one transistor. So transistors are really just a lower level building block for all of these circuit tools and elements. And I would definitely say for circuit designers, it's the most important tool, but sadly 16B only spends like 2 lectures on them. So yeah, that's why we care. Do we have any last questions before I move on? All right, so this is the breakdown of a transistor, and this is mainly the main differences. I think someone asked earlier about the NMOS and the PMOS transistors. So these transistors will always have 3 voltages: the gate, the drain, and the source. And why do we use op amps if you can use a transistor? And I think op amps are really just an abstraction of transistors. So
Wait, could you repeat that? Op amps are a what?
an abstraction of transistors.
Okay.
Yeah. And I think also like op amps, the main difference is that like, I think Seth talked about this in lecture, where transistors have linear regions and nonlinear regions. And op amps in general, you can program them to be linear. So, but I think you can build amplifiers using like fewer transistors than like 13. So it's always better to build something with fewer tools. And I think it's because op amps are much simpler to teach than transistors, which is why we use them in 16A. Anyway, both NMOS and PMOS transistors have these 3 node voltages, gate, drain, and source. And once you apply voltages to these 3 nodes, the switch will either like open or close. And this all depends on this magic quantity, which is VGS, which is the gate voltage minus the source voltage. And for the PMOS, this is V source minus V gate, and the two are opposite. So again, always write these on your cheat sheet. And we have 3 models for the transistor. And we have the switch model, meaning the transistor is just a switch, and it closes whenever this gate to source voltage is greater than the internal threshold. We have the resistor switch, which says it closes again. It behaves like a switch, but we have some internal resistance. And this internal resistance is really kind of just some like undesirable parasitic behavior that just belongs to the transistor. Like we can't do anything about it, but it's just a stronger model. And the RC model also includes a parasitic capacitance. And I think the most important thing for you to know is the use case of each model. So the switch model is really important when you want to analyze the logical behavior of transistors. And by logical behavior, I'm really just talking about these like NOT gates or like AND gates or whatever. And because we don't really care about the resistances there, we just like plug our circuit into a logic gate and see what happens. The resistor switch model is really useful when you want to analyze power consumption. So when you switch these transistors on and off, they'll always consume some amount of power. So the resistor switch model is key for that. And then the RC model is something we'll see, I think, later in the following lectures. I think we'll start looking at it next week, is really to analyze the time delay of each inverter or of each transistor. So if you were to look back at this clock model, if we input something here, let's say you input a true here, it's going to take some time for this true to switch to a false. So that's when we like to use the RC model. And for the purposes of discussion today, I think we'll most likely be talking about just the switch model and resistor switch. We'll just be talking about logical behavior and power consumption. And starting Monday and Tuesday's lecture, you'll be looking at the RC model much more in depth. And I think RC will be the go-to starting next week. Do we have any questions?
Could you explain the NOT gates really quickly that you like keep on referencing? Yeah, those guys.
Yeah. Are you asking like what a NOT gate is, or?
Yeah.
Yeah. So a NOT gate is a basic circuit building block. You have some input and you have some output. And I think the easiest way to understand this is through a truth table, where if you input a true, it's going to just negate that true, and it's going to output a false. If you input a false, it's going to negate that and output a true.
Oh, I see.
Yeah. And what I was trying to say here is if you switch from true to false here through this NOT gate, there's some delay in the transistor that we're going to talk about on Tuesday's lecture, I believe.
Okay, cool. Thank you.
Yeah. Any other questions? And in general, if you ever have a question like while I'm like speaking, always just feel free to speak up. Like, if anything, it makes me feel better about like stuff since like you're actually like checking in with the material. Doesn't the electron flow from source to drain in NMOS? Why would the drain have a higher potential? Yeah, so electron flow is always like something that's like super confusing, where like if electrons flow from source to drain, that means conventional current flows from drain to source, right? So by the passive sign convention, like current flows from, yeah, electrons flow the opposite direction of current. So I think for the purposes of this class, like I would always just like abstract away the idea of like electron flow as like just current. What is the open circle under G in the diagrams? Oh yeah, so this is just a node voltage. And I think the main idea I want to emphasize here is that if you apply some voltage at the gate, let's say we apply like 1 volt to the gate, the switch is either going to be on or off, but this gate voltage is kind of disconnected from the actual circuit or the actual current flow from drain to source. So G just stands for node. That's like disconnected. All right. Do we have any other last questions before we move on?
Sorry, I didn't quite get that. So like when you point at the node voltage symbol, there's a G and then like a circle. What does the circle represent?
It's just like a node. It's like a floating node.
Okay. Okay.
Yeah.
It's just a, okay.
It doesn't do anything to drain to the source. Yeah. And it is, what is parasitic capacitance? It's just capacitance that we don't want, but is like there. It's like a side effect. Yeah. And it is 30 minutes into discussion, but I promise there is a method to the madness that we're going to be talking about the CMOS inverter next. So if you're actually following through the discussion worksheet, I've mainly talked about the first page here on the transistor introduction. We'll spend a little more time talking about the CMOS inverter. And then after that, we'll move on to question 3, which is a single transistor inverter. And if we have time, I don't think we'll have time, we'll move on to the NAND gate. So that's the general roadmap for today's discussion. All right, so one of the main fundamental building blocks in circuits, in digital circuits really, is this NOT gate. And I think we talked about the NOT gate earlier being, if you input a true, you output a false. If you input a false, you output a true. And this inverter here, or the circuit diagram here, represents the NOT gate in circuits. And you might then ask, how do we encode true values and false values into our circuit? So the way circuit designers did this when they were like doing this back in like the 80s, I think, were to define 0 volts as a logical false and VDD some arbitrary high value of like 1 volt. I think in the past it was 5 volts, now it's 1 volt as a logical true. So we're going to define 0 volts as false, VDD as true. And if you're ever curious what VDD stands for like drain, drain. And we're also going to assume that these PMOS and NMOS transistors here have some sort of internal threshold potential. And threshold potential is always something that's like internal within a device. Like you're never going to be asked to calculate what it is. It's just given to you. And it's mainly like based on like the chemistry and the device physics. So we're going to assume that the threshold potential of these 2 transistors are equal to VDD over 2. So as we kind of said earlier, the expected behavior is if we input a true or if we input 5 volts or VDD, we expect V out to be false or 0 volts and vice versa. So we're going to spend some time talking about why this is the case and also just kind of talk about how we actually do this transistor analysis. So the way this is going to work, I'm going to go over how to analyze the PMOS, and then I'm going to put everyone into breakout rooms. You're going to hopefully then talk about the NMOS, and once you figure out both the PMOS and the NMOS, you should be able to solve for V out. So.
Hey, yeah, so what's that middle term in between the 2 equal signs? Like V thresh equals something equals VDD over 2.
V threshold equals, yeah, so, sorry if my handwriting's a little unclear here, but normally we define VTN as the NMOS threshold.
Got it.
And we define VTP as the PMOS threshold. And you might then ask, why did I put absolute value signs around here? And it's because the way circuit designers built these transistors, the threshold of the PMOS is always negative, and it's like hella confusing because like in order for the PMOS to turn on, you got to be more negative than your negative threshold. So I always like to work with positive numbers. So we just take the absolute value, and then whenever V source minus V gate is greater than this absolute value, this will always be positive, will be greater than this absolute value. We say the transistor turns on. Does that help answer the question?
Yeah.
All right. So I'm gonna do a quick analysis. So let's assume Vin is equal to true, which is equal to VDD. Then if we were to look at, just zoom in just to this PMOS transistor, we would see that we have some gate, drain, and some source. And we can identify each of these. So we know that this gate voltage is equal to Vin. We know that the drain voltage is equal to VDD. And we know the source voltage, because if we trace the node here, it's equal to V out. And whenever we want to figure out whether this transistor is on or off, something is wrong here. This is the source, this is the drain. We want to compare the two values. So this is something you always write on your cheat sheet. You write, you want to check whether V source gate, sorry, my audio cut off. Yeah, VTP stands for V. Why do we use VSG instead of VGS and PMOS since VTP is negative? That's exactly why. But since, yeah, so you want to look at this value, V source minus V gate. So you want to compare these two voltages, and then you want to check whether it's greater than or equal to the absolute value of V threshold. So this, it's just an if statement. So V source gate is equal to V source minus V gate, in which case it's equal to VDD minus VDD, which is equal to 0. So then we ask, is 0 greater than the absolute value of V threshold? And the answer is no. So the switch is off or open. Why is Vn equals VDD? I'm just assuming it is. I'm inputting a true value into our inverter. And you could do the exact same analysis assuming Vn is equal to 0. I'm just trying to show that if Vn is equal to VDD, V out's going to be equal to 0. Anyway, so since the switch is open, we can just draw our U circuit, which will look something like this. We have the gate just floating, which is equal to Vn. And then here I'm going to assume switch model. So the switch model tells us that if the switch is open, we just have an open circuit here. So now, what I want you to do, I'm going to split everyone up into breakout rooms, and I want you to analyze the bottom half of this PMOS, or sorry, bottom half of this CMOS, which is the NMOS. And hopefully you should get some other circuit. And based on this, you should be able to tell what V out is. What number is this on the discussion worksheet? This is page 2 of the note. It doesn't
Why
have a
do you
number.
why do you still include the ground node like in the drawing? Like, is there a reason for
The
that?
gate node,
Yeah, or the gate node. Sorry.
really no preference. You could always skip it if you want. I just like wanted to show that like the model here corresponds to like this circuit here.
Okay.
If we wanted to erase it, we could erase it. Yeah.
Okay.
Is it VSG greater than or equal to or greater than? I think it may be greater than or equal to. Like, yeah, so it's greater than or equal to. But normally, like, we don't necessarily like care or look at the behavior when the two are equal. Like, some weird stuff might go on. And also, this is something just good to know, like, for the like, good to know in the real world that like, whenever you say like a voltage is equal to something, it's never actually equal to something. It's equal to something plus noise. So it's a great question, though. I think using greater than or equal to is probably the way to go, but using in the real world, if you were to use greater or greater than or equal to, makes no difference because you always have noise in the real world. All right, so I'm gonna split everyone up into breakout rooms, probably for around 5 minutes. I want you to pretty much do the analysis for the bottom NMOS, solve for V out. Hopefully, you should get V out is equal to 0. And then if you have time after that, I want you to start looking at question 3A, which is on the single transistor inverter. And just a general PSA for breakout rooms. I think the worst feeling for me is like you enter a breakout room. Do we assume Vn is equal? Yeah, you assume Vn is equal to true, equal to VDD. Like the worst feeling is when you just enter a breakout room and everyone's just silent. So if you don't know how to do the problem, just like talk about something else. Like talk about how your day is going. I think my icebreaker that I gave earlier in the 10 a.m. discussion was kind of just to like talk about your like favorite place to study at Berkeley, like when school was open. So yeah, I'll just be dropping around to see if anyone has any questions though. So shit, do I have to delete all these rooms again? This is like hella tedious. All right. But yeah, I'm just gonna open up our rooms. Just feel free to like go over the question or talk about something else. Maybe just talk about how the class is going, or if we're still working on the homework, maybe talk about the homework, but it is Zoom University, so.
Would you be able to re-explain why the threshold voltage is negative? I mean, yeah, for the PMOS.
Do you want me to explain like why it's negative or how to use the fact that it's negative?
Both.
Okay, so why it's negative is really just like something out of scope, but it's like circuit designers just kind of design circuits so that it is negative. Like I don't have too good of an explanation for this one. But how to use the fact that it's negative. So normally we say PMOS is on when VGS is less than the threshold. So since this value is negative, we can put like absolute value signs around it. And that's pretty much where this inequality comes from.
Oh, okay. Thank you.
Yeah, no problem. right, we are back now. Hopefully everyone can navigate their way through Zoom breakout rooms. I only see 28 people here, so. Maybe some people are taking the 60 seconds pretty liberally. I'm actually not sure how to change that. Figure that out later. Were people able to figure out like how to do the analysis for the NMOS? Anyone want to give a stab at it?
Okay, I got this because my breakout group explained it to me.
Yeah, for
But
sure.
basically, so you have V out is off because you have your V in to the NMOS as 0. And since your V in, which
The
is
V in to the NMOS?
yeah, so at the bottom, like I guess in the middle of the CMOS is 0, right?
Well, V in is equal to VDD, right?
Yeah, so you have V in to the bottom of the NMOS, which is VGS, which is VDD.
Yeah, so VGS is VDD, right?
Yeah,
I think perhaps what you were saying is this, right?
yeah. So the NMOS would be on,
Good.
and therefore the switch is open, and you have V out connect to the ground, which is 0.
Yep. That's 100% exactly correct. So idea here is, just to recap, the gate is V in, it's equal to VDD. VGS is equal to VDD, which is greater than the threshold. So the switch is on or closed, meaning current flows from V out to ground. So since current flows from V out to ground, this means V out is connected to ground. So V out is equal to 0 volts. Do you have any questions about the process?
Would it still have worked if VTH was just not divided by 2?
Yeah, so I think if V threshold is like VDD over 3 or 2 VDD over 3, it all works, right? But if V threshold is greater than VDD, for example, then it wouldn't work, right?
Yeah.
And this is kind of a choice of the designer. So the circuit designer needs to be smart and pick a logical high or a true as something greater than the threshold.
Okay, so the minimum your VTH could be is VDD because it's greater or equals for the NMOS.
Yeah, and VTH is always like something internal to the transistor. So normally you pick VDD based on what VTH is.
Okay.
Does that clarify it? Yeah.
So
like
in the in the truth table, the V out, NMOS, and the PMOS all depend on the V in.
Yep.
Okay.
It's because you're inputting something into your circuit and you're getting an output, right?
Yeah.
Yeah.
Wait, so you pick VDD equals 2 times the threshold of the CMOS, right?
Yeah, that's what I did here, yeah. But if you were to pick some smaller VDD, it might like break your circuit, so.
Is there anything special about using a PMOS and an NMOS here? Like could it have been 2 NMOSs, for example?
Yeah, so if you were to have 2 NMOSs here, I think something different, like different behavior would happen. Like I don't remember on the top of my head what would happen. I think, actually, yeah, if you had 2 NMOSs in series like this, it would kind of behave like an AND gate. So does that help answer the question? Like you always pick and choose like these transistors and how to arrange them to build all sorts of logic gates. And we'll actually see in the next question a different way to build a CMOS or a different way to build a NOT gate using just one NMOS transistor. So, all right. Did people get a chance to look at question 3? Isn't that the opposite of what we just showed? If Vn is equal to VDD, NMOS is on, PMOS is off. I think we showed that the NMOS is on and the PMOS is off here. Perhaps on and off may be, I'm not sure where the confusion lies, whether it's an on or off or in something else, but if you're still confused about it, feel free to ask me at the end of the discussion. Okay, so I think for the sake of time, actually, since we only have 5 minutes left, I'll briefly just talk about the single transistor inverter and really the main punchline behind everything. So I think it might be more productive to go over the second part, part B, where we're looking at a transistor here, or an inverter here. This is another NOT gate. And we're using the resistor switch model of the transistor. So this was like that second model we were talking about. It's this model. And the main reason we're doing this is because we want to analyze the power consumption. So first question they ask is, what is V out when Vn is equal to 0? So when we look at the NMOS transistor, we have Vn is equal to 0. This is the gate. This is the drain. This is the source. V out is the drain, and the source is ground. So again, it's just pretty formulaic where VGS is equal to VG minus VS, which is just 0 minus 0, which is equal to 0. And then since 0 is less than the threshold, I forgot to mention that the threshold, I think here they kind of said the threshold is in between 0 and VDD. So since it's less than the threshold, we can say that the NMOS is off / open. So if we were to draw the circuit, the full circuit, this is the result of the PMOS. And then we have everything on top here, which is the VDD and the R1. So since nothing is connected to V out, no current flows from VDD to V out. And this tells us that there's directly a path from VDD to V out. So V out is equal to VDD. Do we have any questions about the process?
So to figure out which nodes are S and D, do you just use the convention that you said earlier, or?
Yeah.
Okay.
I would mainly just try to follow these conventions here. But normally if you're unsure as well, I think source will always be the lower potential for the NMOS and drain will always be the higher potential. So why do we consider the NMOS?
Go ahead.
To be a resistor if the switch is off. And the resistor is here, but nothing's connected to it, so it doesn't affect our circuit at all. But it'll be important in the next part where the switch is on, so I just left it there. Does that help? And I think to conclude the analysis here, we do the exact same thing. So if we were to just label these steps, step 1 is really to label all the nodes G, D, and S. And again, why does it matter if IR1 is equal to 0? I think if there were some current flowing through here, then V out would be like VDD minus IR1 times R1. That's the only reason. But we label all the nodes. We know that the gate is equal to Vin, which is equal to VDD. We know the source is equal to 0, and the drain is equal to V out. So then VGS is equal to VDD, and this is now greater than the threshold. So the NMOS is on or closed. And this tells us that there in fact is some like current flowing from drain to source here. And in fact, if we were to do the actual analysis, then we know that using voltage dividers, that V out is equal to Rn all over R1 plus Rn times VDD. And if you actually plug in the math of like, the question tells you that like Rn is equal to 1 over 10 R1, that it's equal to like 1 over 11 VDD. And I think the important caveat to notice here is that when we input a true, we expect a false, right? Because it's supposed to behave like a NOT gate. But notice how we haven't really achieved a true 0. We achieve something very close to 0, but it's not exactly equal to 0. So that's one of the downsides or the fallbacks of this resistor switch model. And yeah, so it's not really a NOT gate. If you were to actually set some like threshold boundaries, like if you were to call like anything less than like, I don't know, let's say you label false as like V less than 1 over 10 VDD, then it would behave like a NOT gate. It all depends on the designer, like how you define true and false, but just notice that it doesn't reach the true 0.
Wait, sorry, I think I missed this. How did you get the Rn in like the S near the S node? I know you did that in the previous part as well, but I think I missed that. Yeah.
Where did this resistor come from?
Yeah.
It's from the resistor switch model here of the NMOS transistor.
Okay.
We're just,
So is
yeah,
there like a derivation for this, or are we just supposed to like use it?
just use it. Like,
Okay.
assume the NMOS has some internal resistance. And I think one of the main themes in this class is like, sometimes like there's so many like proofs, definitions, theorems, like just use whatever results are given to you. Like we're engineers here, so.
Okay, thank you.
I think the last takeaway that I really wanted to get to, although we're running a little late here, it's 12:03, is how much power does the circuit consume? And remember that power is equal to I times V. And since I in the circuit is equal to VDD all over R1 plus Rn, power is equal to VDD squared all over R1 plus Rn. And we're dissipating power because current is flowing in our circuit now. And I think this is the main downside of this single resistor switch model, because whenever, like, you never want to consume power in your circuit. Like, you always want to minimize power. Power is something bad because, like, whenever you consume power through a resistor, it dissipates as heat. And this is kind of the reason your phones always like get so hot when you charge them. So power is bad. If the circuit is not connected to ground, then there is no current. If the circuit is not connected to I think the best way to explain this is if there's no closed loop in your circuit. So, for example, if I were to attach a small load to the circuit, then current would flow. But right now, actually, I'm going to take the case where, yeah, we had this open circuit here. So essentially, if we have nothing here, no current flows since it kind of leads into a floating node. But if we attach a load, then current flows. And if we detach and attach, so on and so forth.
So do we assume, oh, sorry, did I cut you off?
No, go ahead.
Oh, do we assume all MOSFETs have internal resistance and capacitance then?
Yeah.
Okay.
They will always have some internal resistance capacitance that's kind of parasitic.
Okay.
And it really leads into the later model. So we use this model when we analyze power. We use this model when we analyze logical behavior.
Okay. So then is there a reason like why we didn't like take the capacitance in this problem?
I think it just complicates our circuit. That's literally the only reason.
Okay.
It behaves the same way though.
Okay. So what would be like told, like, let's say like on a test or something, when we should take each of them into account?
Yeah.
Okay, cool.
And when in doubt, always use like RC.
Okay.
And normally they'll give you some resistor and capacitor value anyway. So
okay,
it should be clear from context.
Cool.
So just to conclude, I think summary, like main takeaways from today. Since things did go by really fast, like there are 2 transistors. You have the PMOS and you have the NMOS. And they behave like switches, as we kind of saw in the entire discussion today. And the second big idea is that we can build logic gates out of transistors. So we kind of saw how this like NOT gate is equivalent to this CMOS inverter. And it really gives us a way to like, I guess like look at the internals of logic gates. And lastly, the CMOS inverter is desirable, and I didn't have enough time to like talk about this in full, over single NMOS. So if we're comparing this model here to the CMOS that we spent all our time on, since CMOS consumes no power or 0 power, when no load is attached. So I think those are the main takeaways for today. 2 transistors. You can always build logic gates out of them. I think if you have time later after the discussion, you can take a look at question 4, which is on a NAND gate, and it's like basically the same thing that you did in this like review over here. And lastly, transistors always consume power when they switch on and off. So like we always want to somehow like use this complementary behavior of P and N to like consume as little power as we can. And then lastly, I think this is like looking forward to like Tuesday's lecture and Wednesday's discussion. Transistors always have delay. And what I mean by this is like all the way back at the beginning, we kind of talked about how like we have this like ring oscillator switching from like a true to a false here, there will be some delay associated. And that's because of this parasitic capacitance here. So, all right, I am 10 minutes over, but if you still have any questions, feel free to ask. And thanks for coming out to discussion today. Does the NMOS consume website linked? I'll link it in Piazza later, yeah. Does NMOS consume power anyway when the switch is off, no load is attached? So over here, notice how even though we attach nothing to the load, we're still consuming power. Yeah, so actually I'm gonna answer, Daniel, does that help answer your question or? Yeah, so when we attach something here, we'll consume additional power as well. But like, the point is, even if you just leave it as on or off, and just to look at this input-output behavior, it would always consume power. And to answer Victor's question, when would we use the RC model? The RC model is really to understand the time delay of each transistor. So we'll see later in, I think, Tuesday's lecture that if we have this NOT gate, it takes some time to switch from true to false. And that's because like this capacitor is kind of slowing our circuit down. The number 3 answer is whether Vn is equal to 0 or yeah, so I guess technically, if we were to answer this, in the first phase, since no current flows, no power is consumed. But here, since current is flowing, we consume this amount of power. So when you switch from true to false, you consume some power. But if you switch from false to true, you don't consume any power.
Isn't current flowing through R1 though? So wouldn't that consume some power?
Are you asking about this current?
Yeah.
But since nothing's connected to the output, it's equal to 0.
Oh, I see.
Yeah.
Okay.
And CMOS, yeah, so if you were to actually do the analysis with CMOS, you would see that no current flows in your circuit. It's doing all this switching without any current. That's like the magic of PMOS or CMOS. If you were to actually like look here, like one switch will always be open, one switch will always be closed. So as a result, no current flows. Yeah, which is kind of cool. But as always, if you add a load, current will form. So yep, no current is equal to no power. And why is that? P equals IV. All right. If we don't have any other questions, I'll stop the recording for now since we are way over time.